Welcome back to the deep dive. Today, we are tackling a system that really dictates the rhythm of your entire existence. We are looking at what is essentially the volume knob of the human brain.
That is a great way to frame it, because we tend to think of consciousness as a simple light switch. You're either awake or you're asleep, on or off.
Right.
But the pharmacology we're covering today really proves that's completely wrong.
It's not binary at all. It's a spectrum. And today, we are diving into Pharma 19, Hypnotics and Sedatives, calming the overactive brain. We're synthesizing the two heavy hitters, Katzim's basic and clinical pharmacology, and Goodman and Gilman's the pharmacological basis of therapeutics.
The classics.
Exactly. And our mission, really, is to understand how we can chemically turn down the noise, the arousal in the brain, without accidentally shutting off the power grid entirely.
And that really is the central tension of this entire field. It's the core problem. How do you dampen anxiety, that overactive network state we're talking about, without stopping something essential like the respiratory drive?
Or how do you induce sleep without creating, well, a coma? It's an incredibly delicate balance.
It is.
So before we dive into the molecules and the mechanisms, let's define the battlefield. We're dealing with sedatives and hypnotics. In, common parlance, people use these terms interchangeably all the time.
They do, but for us, in the literature, they have distinct functional definitions. And you really need to get this clear from the start.
Okay, so let's start with sedative. What's the precise definition?
A sedative is specifically designed to decrease activity, to moderate excitement, and really to exert a calming effect. The goal is what we call anxiolysis, getting rid of anxiety.
And crucially.
And crucially, a good sedative should do all of that with minimal effect on your motor function or your mental acuity. The goal is to be calm, not clumsy or confused.
Okay, calm, not stupid. Got it. So that's a sedative versus a hypnotic.
Right. A hypnotic has a much more aggressive goal. The point of a hypnotic is to produce drowsiness and to facilitate the onset and, just as importantly, the maintenance of a state of sleep.
And not just knocking someone out.
No, absolutely not. We want it to resemble natural physiological sleep, the kind of sleep that if you hook the person up to an EEG, the brain waves would look, well, pretty normal.
But here's the catch, and I think this is the first big takeaway from Katzung. These usually aren't two different buckets of drugs. They're often the exact same drug, just at different spots on the dose-response curve.
Exactly. It is a dose-dependent continuum. This is what the textbooks call the gradient of CNS depression. It's a fundamental concept.
So walk us through that gradient.
Okay, so at a low dose, let's say drug X is a sedative, it just takes the edge off your anxiety.
You feel calm.
Right. Then you double the dose. Now, that same drug X is a hypnotic. You're getting drowsy, you're falling asleep.
Okay.
Double it again.
And now you're in the territory of surgical anesthesia.
You are. And if you keep pushing that dose higher, you hit coma and eventually respiratory arrest and death. The difference between a sleeping pill and a lethal injection is often just the amount of powder in the capsule.
That's a sobering thought. And it brings us right to our roadmap for today. We're going to break this down into 6 distinct territories to really map this out properly for you.
Sounds good.
First, we have to look under the hood at the engine of all of this, the GABA receptor. This is the molecular brake pedal of the brain.
Then we'll move on to what we're calling the selectivity revolution, how we went from the dirty drugs of the past, the blunt instruments, to the more targeted smart drugs of the present.
After that, we'll do a deep dive into pharmacokinetics, specifically why the liver is the ultimate gatekeeper for these drugs and why some leave you with that awful hangover feeling while others don't.
We also absolutely need to talk about sleep architecture. Are we actually fixing sleep with these drugs, or are we just knocking people unconscious? Because those are two very, very different things.
A crucial distinction. Then we'll look at the novel agents, the newer drugs that don't even touch GABA at all, a completely different approach.
And finally, we have to cover the dark side. Tolerance, dependence, and the lethal synergy of mixing these drugs with other depressants.
It is a massive topic.
It is, but I promise if you really understand the core mechanism, all the clinical decisions, all the side effects, they just fall into place and make perfect sense.
So let's start with that mechanism. Section 1, the molecular brake pedal. If you want to slow down the brain, you have to talk about GABA.
Gamma-aminobutyric acid, GABA. It is the major inhibitory neurotransmitter in the central nervous system. Full stop.
So it's the main off signal.
It is. I like to think of the brain as a crowded, noisy room where everyone is talking at once. Glutamate is the guy shouting, trying to get everyone excited and riled up.
The excitatory signal.
Right, and GABA is the little librarian walking around going, shh, tell people to quiet down.
I like that. And the mechanism of that shush is fascinating. We are focusing on one specific receptor type, the GABA receptor. Can you paint a picture for us? Structurally, what are we looking at?
Okay, visualizing this is absolutely key. Imagine you're looking at a cell membrane, the fatty wall of a neuron. Embedded in it is this big, complex protein that looks kind of like a rosette or a donut.
A donut.
Like it's a pentamer. That means it's built from 5 distinct protein subunits that are arranged in a circle. And right through the middle of that donut, there's a hole. That hole is an ion channel.
And this channel is exclusive. It's got a very specific bouncer at the door. It only lets one thing through.
Exactly. Chloride ions, Cl-.
Okay, let's apply some, basic cell biology here to really understand the sedation. A neuron is basically a tiny salty battery. It's got a voltage difference across its membrane, the membrane potential.
That's right.
So when this GABA channel opens and all that chloride rushes in, what happens to the battery?
So remember, chloride is a negative ion. It's got a negative charge. When GABA binds and opens the gates, chloride flows down its electrochemical gradient, which means it rushes into the cell. You are flooding the interior of that neuron with negative charge.
So you're making the inside more negative.
You're making it more negative. You're driving the membrane potential down. We call this hyperpolarization. If the normal resting potential was, say, negative 70 millivolts, maybe now it drops to negative or even negative 90 millivolts.
And what does that do functionally?
It moves the neuron further away from its firing threshold. It makes it significantly harder for any excitatory signal, any glutamate, to get that neuron to fire an action potential.
You're essentially locking the trigger. You're putting the safety on.
Precisely. You are stabilizing the neuron in a resting, inhibited state. You're shushing it.
Okay, that makes sense. Now we have 2 major historical classes of drugs that manipulate this system, the benzodiazepines and the barbiturates. But, and this is key, they do it in fundamentally different ways. Let's start with the benzodiazepines drugs you've all heard of, like diazepam, Valium, alprazolam, Xanax, lorazepam, Ativan.
These are, without a doubt, the most widely used anxiolytics and sedatives in history. But here is the nuance that saves lives, the thing you absolutely must remember. Benzodiazepines do not open the chloride channel themselves.
Wait a second. If they don't open the channel, how do they work? I thought they were like GABA agonists.
No, and that distinction is so critical for safety, for board exams, for everything. They are positive allosteric modulators.
Allosteric, meaning other site.
Correct. So imagine the GABA receptor has a specific main parking spot for GABA. That's the key ignition slot. Benzodiazepines have a completely different parking spot on the protein, a separate site located specifically at the interface between an alpha subunit and a gamma subunit.
So the benzo parks in its own little side lot. Then what happens?
When the benzo binds to its unique spot, it causes a conformational change, a subtle shapeshift in the entire receptor protein. This shapeshift makes the main GABA parking spot stickier.
Oh.
It increases the affinity of the receptor for GABA.
So it's not replacing GABA, it's making the body's own natural GABA work better. It's an amplifier.
Exactly. It amplifies the natural signal. So if you have a little bit of GABA floating around in the synapse, the benzodiazepine makes the channel respond as if there were a lot of GABA present.
And this is the ceiling effect that Katsung talks about.
This is the ceiling. If there's zero GABA being released, if the librarian is on a coffee break, the benzodiazepine does absolutely nothing.
That is a built-in safety valve.
It is the most important safety valve. It's why you can take a massive dose of Valium, and while you'll be very, very asleep for a long time, you probably won't stop breathing. Because eventually, the system just runs out of natural GABA to amplify. The effect hits a ceiling.
Now, let's contrast that with the barbiturates, drugs like phenobarbital, pentobarbital, thiopinol. You called them the heavy hammers earlier.
The heavy hammers, the blunt instruments, they are a relic of a more dangerous time in medicine. Now, they also bind to an allosteric site on the receptor, but it's a different one from the benzos.
And at low doses, they act similarly.
At low doses, they also facilitate GABA's action. They help GABA bind and open the channel. But at high doses,
the safety valve blows off.
Completely. At high concentrations, barbiturates become GABA mimetic. That's a key term. It means they can pop the chloride channel open directly, even if there is absolutely no GABA present in the brain.
So they don't need the key anymore. They just kick down the door.
They kick down the door, and then they hold it open. And to make matters even worse, At those high concentrations, barbiturates also block excitatory AMPA receptors for glutamate.
So they're double dipping. They're boosting the shush signal and blocking the shout signal.
Exactly, stomping on the brake and cutting the fuel line at the same time.
And this explains the linear dose-response curve that's so prominent in the textbooks.
Yes. With barbiturates, there is no ceiling. You increase the dose, you get deeper sedation. You increase it more, you get surgical anesthesia. You increase it more, you get coma. You increase it more, you get death. That linearity is what makes them so incredibly dangerous in an overdose.
Which is why they were, a common method for suicide for decades before benzodiazepines became more widely available.
Sadly, yes. The margin of safety is just too narrow.
There's one more really elegant distinction that Goodman and Gilman highlights, and it's about the way the channel opens. It's this concept of frequency versus duration.
Ah, yes. This is classic, beautiful pharmacology. So, benzodiazepines increase the frequency of the channel opening events. They make the gate flutter open more often in response to GABA.
Okay, so more frequent but short openings. I've heard the mnemonic, Ben likes it frequent.
Chuckles. If that helps you remember it, absolutely. Benzos, frequency. Barbiturates, on the other hand, they increase the mean open duration.
So when the channel opens, they prop it open for longer.
Exactly. They hold the gate open for a longer period of time. So Barb likes it long.
So benzos equal more flutters, barbs equal a longer, sustained opening. Both result in more chloride getting into the cell and more inhibition, but the biophysics, the actual protein dynamics are completely different.
Correct. And that holding the door open action by barbiturates is a much more forceful, profound intervention on the protein's function.
Okay, let's just unpack this receptor structure a little bit more, because I feel like we breezed past it, but this is the key to the next section. You said pentamer, 5 subunits.
Yes, 5 individual proteins coming together. And it's not just a random jumble. There's a very specific architecture. The most common arrangement in the adult human brain is 2 alpha subunits, 2 beta subunits, and 1 gamma subunit.
And you can visualize them arranged in a circle, right?
Exactly. Think of them alternating. Alpha, beta, gamma, forming this ring with the channel in the middle.
And you said the binding sites are at the interfaces, like the cracks between the cushions of a sofa.
Perfect analogy. The GABA molecules themselves, and you actually need 2 molecules of GABA to activate the receptor, they bind at the interfaces between the alpha and the beta subunits.
So GABA parks between an alpha and a beta.
Correct. But the benzodiazepine binding site, that allosteric modulator site we've been talking about, is at a totally different location. It's at the interface between an alpha and a gamma subunit.
Ah, so this explains why you need a gamma subunit for benzodiazepines to work.
Yes, absolutely. This is a crucial point. If a particular GABA receptor is built, say, just from alphas and betas, GABA will work on it just fine. But a drug like Valium will just bounce right off. It has nowhere to park.
And does that actually happen in the brain?
It does. There are some GABA receptors, for instance, that have a delta subunit instead of a gamma. Those receptors are completely insensitive to benzodiazepines.
Wow, that's a deep cut. So the specific subunit composition, the geography of these different receptor types in the brain, dictates where a drug acts and what it does.
Exactly. It's not just about the drug. It's about the specific flavor of receptor that's present in a given neural circuit. And this leads us directly into our next section, the selectivity revolution.
Section 2, because not all GABA receptors are the same. We've established the basic pentamer structure, but you can mix and match the parts, right? There are different types of alpha subunits, different betas.
Right. It's like a biological Lego set. You have multiple versions of each subunit. There are 6 different types of alpha subunits known in humans, alpha double 1 through alpha 6 setters. There are different betas, different gammas. And the specific type of alpha subunit you have in that pentamer changes everything about what that receptor does.
And this is what we're calling the Rosetta Stone of subunits. It allows us to decipher the different effects of these drugs. Let's break down the 2 main teams here, Team Alpha 1 and Team Alpha 23.
So through some really elegant genetic work with knockout mice, scientists were able to figure this out. They found that the alpha delta 1 subunit is, for all intents and purposes, the sedative button.
Alpha 1 equals sedation.
Receptors that contain the alpha delta 1 subunit are the ones that mediate sedation, the hypnotic or sleep-inducing effect, and also that anterograde amnesia, forgetting what happens after you take the drug.
The blackout effect.
Exactly. They also seem to mediate ataxia, that wobbliness and lack of coordination.
Okay, so Alpha 1 is the big knockout button. What about Alpha 2 and Alpha 3?
Those are what you could call the chill buttons. The anxiolytic or anti-anxiety effects seem to be primarily mediated by receptors containing the alpha-22 and alpha-3 subunits, and so are the muscle relaxant effects.
Okay, so logically, if I have a patient with, say, generalized anxiety disorder, what I really want is a drug that hits alpha-2 and alpha-3.
Right.
But I probably don't want to hit alpha-1 because I don't want them falling asleep at their desk or forgetting their commute home.
That is exactly right. That has been the holy grail of pharmacology in this area for decades, to create a selective anxiolytic without sedation.
But the traditional benzodiazepines like diazepam, lorazepam, they don't do that.
No, they're non-selective. They're dirty. They hit pretty much everything, alpha-1, 2, 3, and 5. And that's why when you take a Valium for anxiety, you also get sleepy. That's the alpha-1 effect. And you might forget where you put your keys, also alpha-1. It's a package deal. You can't separate the effects.
Okay, so this brings us to the Z compounds. Drugs like zolpidem, Ambien, Zolpidem, and isobuprofen. These came out in the 90s and were marketed as the better sleeping pills. Why? What was the breakthrough?
The breakthrough was selectivity. These drugs were designed, or discovered, to have a much higher affinity for the alpha-1 subunit.
The sedation subunit.
Precisely. They bind preferentially to GABA receptors that contain the alpha-1 subunit. Structurally, they look nothing like benzodiazepines, but they bind to the same site.
And what's the clinical implication of that selectivity?
It makes them excellent hypnotics. They are very effective at inducing sleep because they are targeting the main sleep subunit. But because they have very weak affinity for the alpha-2 and alpha-3 subunits, they have much less of an anti-anxiety or muscle relaxant effect at normal therapeutic doses.
This explains perfectly why a doctor would prescribe zolpidem for insomnia, but it would be completely useless for treating a panic attack or a muscle spasm.
Correct. The drug's function is dictated by its receptor selectivity. And, at least in theory, this selectivity for alpha-1 should also mean they cause less disruption to the overall architecture of sleep, which we'll definitely circle back to.
We have to talk about the weird side effects of the Z drugs, though. I mean, we've all heard the horror stories. People on Ambien, sleep driving, sleep cooking, entire meals, sleep shopping on the internet. What is going on there?
It's a fascinating, if also terrifying, parasomnia. The thinking is that because Z drugs hit that alpha-1 subunit so hard and so selectively, they very effectively trigger the hypnotic state and the amnesia.
Okay, so the brain's recording and consciousness centers are offline.
Right, but because they don't hit the other subunits as broadly, or perhaps because of the specific distribution of alpha-1 receptors in the brain's motor circuits, the pathways for complex motor tasks aren't fully suppressed in the same way they would be with a non-selective benzo.
So you get this dissociation.
A complete dissociation. You have a brain that is offline for conscious awareness and memory formation, but online for performing complex, ingrained motor tasks.
The lights are on, the body is moving, but the pilot has definitely left the cockpit.
And the black box flight recorder is switched off. The person wakes up the next morning with absolutely no memory of buying a horse on eBay or driving to the next town over.
That is genuinely terrifying.
It is. It's a serious risk. And it led the FDA to actually lower the recommended starting dose for zolpidem, especially for women.
Why specifically for women? What's the difference there?
It comes back to pharmacokinetics, which we'll get into more detail on. But essentially, women tend to metabolize and clear zolpidem from their system more slowly than men.
So the drug levels stay higher for longer.
Exactly. So if a woman took the standard 10 milligram dose at 11 p.m., she might still have enough active drug in her bloodstream at 7 a.m. the next morning to significantly impair her driving, even if she feels awake.
Wow. So a simple difference in metabolic rate completely changes the safety profile of the drug.
Pharmacology is always personal. Population averages can be very misleading.
Before we move on from the receptors, we have to talk about the antidote, the reversal agent. If someone presents to the ER with an overdose on these drugs, is there a magic button we can push to reverse it?
For some of them, yes. The drug is called flumazenil.
Flumazenil, how does it work? What's the mechanism?
It is a competitive antagonist at the benzodiazepine binding site. It has a high affinity for that same parking spot we talked about, the one between the alpha and gamma subunits, but when it binds, it does nothing. It has no intrinsic activity.
It's a blank key.
It's a blank key that gets stuck in the lock. It just sits there and physically blocks the benzodiazepines or the Z drugs from binding.
So you give it to someone in a benzo-induced coma and they just wake up.
It's incredibly dramatic. You give a dose of IV flumazenil, and someone who is completely unresponsive can sit up and start talking to you within a minute.
But, and this is a huge but, that always comes up on exams, it does not reverse an overdose from barbiturates or alcohol
And why not?
because they bind to different sites.
Exactly. Flumazenil is highly specific to that one benzodiazepine binding site. Barbiturates have their own site. Alcohol has a whole complex mess of mechanisms. So if your patient took a bottle of phenobarbital or drank a fifth of vodka, giving them flumazenil is completely useless.
And isn't there also a major risk with giving flumazenil, say, to someone who is physically dependent on benzodiazepines?
Yes, this is the other critical caveat.
Yeah.
If you give flumazenil to someone who's been taking high-dose Xanax every day for a year, their brain has adapted to the constant presence of that drug.
You're ripping away the safety blanket.
Instantly. You precipitate an immediate severe withdrawal syndrome. You can induce status epilepticus nonstop seizures. So you have to be incredibly careful. It's not just a get-out-of-jail-free card you can hand out to everyone.
So its use is really limited to, say, reversing sedation after a minor procedure like an endoscopy, or in a confirmed acute overdose in a patient you know isn't a chronic user.
Exactly. It's a precision tool, not a blunt instrument.
Okay, let's shift gears now to Section 3, clinical pharmacology. We've talked a lot about the receptors, but a drug is useless if it can't get to the brain, and then once it's done its job, the body has to get rid of it. This seems to be where the real art of prescribing comes in.
Absolutely. The pharmacokinetics, absorption, distribution, metabolism, and excretion are what dictate which drug you choose for which clinical scenario. It's not just about picking a sedative, it's about picking a drug with the right timing.
Let's start with absorption and onset of action. Why does a drug like triazolam hit you like a freight train, while something like oxazepam is more of a slow burn?
It really comes down to one word: lipophilicity, fat solubility.
Okay.
The blood-brain barrier is essentially a wall of fat. The brain itself is a big ball of fat. So drugs that are highly lipophilic, highly fat-soluble, can zip across that barrier incredibly fast and get into the CNS. Triazolam is very lipophilic.
So it's absorbed rapidly from the gut and enters the brain almost immediately.
Yes. That makes it great for initiating sleep if someone has trouble falling asleep. It hits hard and fast.
Let's talk about an extreme example of that. Thiopental, the barbiturate. We used to use this for inducing anesthesia. You inject it intravenously, and the patient is unconscious in what, seconds?
A single arm-brain circulation time, 10, 15 seconds.
But then they wake up just a few minutes later. Why? Did the body metabolize the drug that fast?
No, and this is such a key concept. It's not metabolism, it's redistribution.
Redistribution, what does that mean?
Okay, so you inject this highly lipophilic drug. It goes into the blood. The brain gets a huge proportion of your cardiac output, so the drug floods into the brain first, causing rapid anesthesia.
Right.
But the drug is still circulating in the blood. And over the next few minutes, it starts to leave the blood and distribute into other body tissues. First to other well-perfused organs, but then to the big, slower compartments, like muscle and especially fat.
So it's seeping out of the blood and hiding in the muscles and fat tissue.
Exactly. And as the drug moves into these peripheral compartments, the concentration of the drug in the blood drops. This creates a gradient, and the drug starts to leave the brain and go back into the blood to be carried away to the fat. As soon as the brain concentration falls below the anesthetic level, the patient wakes up.
That is wild. So the drug is still fully present in their body. It's just been redistributed away from the target organ.
Precisely. The termination of the effect is due to redistribution, not metabolism.
Okay, now let's talk about that metabolism, the liver. You call this the metabolism trap, and I feel like this is where so many prescribing errors happen in practice.
It is. The vast majority of sedative hypnotics are metabolized by the liver, specifically by the cytochrome P450 enzyme system, mostly an enzyme called CYP3A4. But here's the trap. Many benzodiazepines are not just broken down into inert waste products. They're broken down into other active drugs.
The zombie metabolite effect.
Exactly. Let's trace the path of a classic drug like diazepam, Valium.
Okay, walk us through that cascade. What happens after you swallow a Valium?
So you take diazepam. The liver CYP enzymes act on it through a process called oxidation, and they turn it into a new molecule called desmethyldiazepam, also known as nordiazepam.
And this new molecule is active.
It's very active. And worse, it has a massive half-life. We're talking 40 to 100 hours.
100 hours. So it's hanging around in your body for days.
For days. But it doesn't stop there. The liver then takes that desmethyldiazepam and slowly converts it into another active metabolite, oxazepam. which is also active, though with a shorter half-life.
It just keeps going. It's like a Russian nesting doll of active drugs.
It is.
Yeah.
So think about the clinical consequence. If you give an elderly patient a dose of diazepam tonight to help them sleep,
Yeah.
a huge chunk of that active 100-hour half-life desmethyl diazepam is still in their system tomorrow night when you give them the next dose.
So it stacks. It accumulates.
Stacks and stacks. We call this the cumulative effect. After a week of nightly use, that patient might be walking around in a fog all day, confused, at risk of falls, because their blood levels of active drug are constantly rising. This is the so-called hangover effect. It's not a hangover. It's just residual drugs still working.
And this is particularly dangerous for the elderly, right?
Extremely dangerous. Two reasons. First, as we age, our liver's phase 1 metabolic reactions, those oxidation reactions done by the CYP enzymes, they slow down significantly, so they clear these drugs much more slowly.
Okay. And the second reason?
Body composition. Elderly patients tend to have less muscle and a higher percentage of body fat. Since these drugs are lipophilic, they have a larger volume of distribution to hide in. Both of these factors dramatically increase the half-life. The half-life of diazepam in an 80-year-old can be several days.
So if you have an elderly patient or someone with significant liver disease, what's the solution? You can't just tell them to suffer through their anxiety or insomnia.
So you use the ology drugs.
You know.
LOT, lorazepam, oxazepam, and temazepam.
LOT. Okay, why are those three different?
Because they have a much cleaner metabolic pathway. They essentially skip that messy, dangerous phase 1 oxidation. They don't rely on the CYP enzymes.
So what do they do instead?
They go straight to phase 2 metabolism, which is called conjugation. The liver just takes the drug molecule and directly attaches another molecule to it, usually glucuronic acid, which makes it water-soluble and easy for the kidneys to pee out.
And phase 2 metabolism is better preserved in the elderly.
Remarkably well preserved, yes. Even in old age and moderate liver disease, conjugation works pretty well. Plus, and this is key, the conjugated metabolites are inactive. There are no zombie metabolites. What you see is what you get. When the body processes lorazepam, it's done.
That is a crucial clinical pearl. Old liver or bad liver, think LOT drugs. Lorazepam, oxazepam, temazepam.
Absolutely. And there's one more pharmacokinetic interaction we have to mention. Enzyme induction. This is the other big reason barbiturates fell out of favor. A drug like phenobarbital is a potent inducer of hepatic enzymes.
It revs up the liver's machinery.
It actually causes the liver to synthesize more CYP enzymes. So if you're taking phenobarbital regularly, your liver becomes this hyper-efficient drug processing plant.
And that's bad because
Because it starts chewing up other drugs you're taking much faster than normal. It can make your warfarin ineffective, leading to a clot. It can make your birth control pills ineffective, leading to an unplanned pregnancy. It just wreaks havoc on your other medications.
Whereas benzodiazepines and Z-drugs don't do that.
Generally, no. It's another major point in their favor from a safety and drug interaction perspective.
Okay, this is a great place to shift. Let's move to section 4. Sleep architecture. We're giving these drugs to help people sleep. But the big question is, are we giving them good sleep?
That is the million-dollar question, isn't it? The goal of treating insomnia is to provide restorative sleep. But the reality is that most sedative hypnotics, especially the older ones, significantly distort the natural architecture of sleep. We are often just manufacturing a state of unconsciousness that looks like sleep from the outside.
So we know normal sleep isn't monolithic. It has stages. Stage 1, stage 2, then slow wave sleep or deep sleep, and finally REM or rapid eye movement sleep. What do the classic benzodiazepines do to this map?
They do a few predictable things. First, they decrease sleep latency. That's a good thing. It means you fall asleep faster.
Okay.
Second, they increase total sleep duration. You sleep for longer. But, and this is a big but, that extra time is spent almost entirely in stage 2 and REM sleep.
Which is the lightest stage of real sleep.
It's a lighter stage, yes.
Yeah.
And here's a trade-off. To give you more stage 2, they steal time from the other stages. They consistently decrease REM sleep, and most importantly, they decrease slow wave sleep, which is stage 3 and 4.
Wait a minute. Isn't slow wave sleep the physically restorative deep sleep where your body repairs itself? And isn't REM the mentally restorative sleep where memory consolidation happens?
Yes, you are sacrificing the most important, most restorative stages of sleep. So you might get 8 hours of sleep on the clock, but it's a shallow, unfulfilling sleep.
It's like eating 2,000 calories of iceberg lettuce. You feel full, but you're not actually nourished.
That's a fantastic analogy. And this is why people can feel groggy and unrested even after a full night on a benzo. And when you stop the drug abruptly, you often get REM rebound.
What's that?
Because your brain has been starved of REM sleep. The first night or two without the drug, it tries to cram it all in. You get these long periods of intense, vivid, and often terrifying nightmares.
So did the selective Z drugs fix this problem?
They're better, but not perfect. Zolpidem, for example, does decrease REM sleep a bit, but it seems to have a minimal effect on slow-wave sleep, which is a big improvement over the benzos. That's why it subjectively feels a bit more restorative for many people.
What about azopiclone?
Azopiclone definitely increases total sleep time, but again, that's mostly by increasing stage 2. At higher doses, it also suppresses REM. So again, better, but not a perfect replica of natural sleep.
This all makes a pretty compelling case for looking at other mechanisms.
It does. Which is a perfect segue. Section 5, Beyond GABA. We've been obsessed with this chloride channel for almost the whole deep dive. But what else is in the pharmacologist's toolbox?
Well, you said earlier, if GABA is the brain pedal.
We can also mess with the master clock for the whole system, or we can block the gas pedal.
The clock, that has to be melatonin.
Exactly. We have drugs like Ramiltian and Tasmiltian. These are melatonin receptor agonists. They don't touch GABA. Instead, they bind to MT1 and MT2 melatonin receptors in the suprachiasmatic nucleus of the hypothalamus.
The SCN, the brain's master clock.
Right. So these drugs don't globally depress the central nervous system. They're not sedatives in the classic sense. They just send a powerful signal to the brain's clock that says, hey, it's nighttime, time to start the sleep process. They help to shift the circadian phase.
So Ramiltian is really just for sleep onset insomnia. It helps you fall asleep at the right time, but it doesn't really knock you out or keep you asleep if you have other issues.
Correct. And because of this mechanism, it has essentially no abuse potential, no withdrawal symptoms, and no rebound insomnia. It's very, very safe. The downside is that it's not very powerful. If you have severe anxiety-driven insomnia, Ramiltian might feel like taking a sugar pill. It's subtle.
Tasmiltian is interesting. It's approved for non-24-hour sleep-wake disorder in people who are totally blind.
Exactly. Because they have no light perception, their internal clock can't synchronize with the 24-hour day. Their sleep-wake rhythm just drifts. Tasmiltian helps to lock it into a normal cycle.
Okay, so that's the clock. Now for the gas pedal. You mentioned orexin.
Orexin, which is also called hypocretin, is a neuropeptide produced in the hypothalamus. And its job is to promote and stabilize wakefulness. It's the chemical signal that keeps you alert and awake during the day. In fact, the disease narcolepsy is caused by a loss of the neurons that produce orexin.
So the theory behind an insomnia drug would be that people with insomnia have an overactive orexin system.
That's the idea. So we now have drugs called orexin antagonists, like suvorexant. They work by blocking the orexin receptors.
I love the conceptual shift here. The entire GABAergic strategy is press harder on the brake. The orexin strategy is take your foot off the gas.
It's a beautiful way to put it. You're turning off the stay awake signal rather than trying to force the go to sleep signal.
And finally, let's talk about the real oddball in this group, at least for anxiety. Buspirone.
Buspirone is completely unique. It is an effective anxiolytic, but it has zero hypnotic, sedative, or euphoric effects, no muscle relaxation, no anticonvulsant properties.
How is that even possible?
Because it doesn't touch the GABA system at all. Its primary mechanism is as a partial agonist at 5-HT1A serotonin receptors. It works by modulating the serotonin system, not the GABA system.
So what's the catch? It sounds like the perfect anti-anxiety drug.
The catch is timing. A benzodiazepine provides anxiety relief in about 30 minutes. Buspirone has a delayed onset of action. It takes 1 to 2 weeks, sometimes longer, to start working.
So it's completely useless for a sudden panic attack.
Utterly useless. But for generalized anxiety disorder, GAD, that chronic low-level worry where you need long-term management without sedation, cognitive impairment, or addiction risk, it can be a fantastic option.
So buspirone is the slow cooker of anxiety relief, whereas benzos are the microwave.
And just like a microwave, if you're not careful, benzos can burn you.
Which brings us to our final section, Section 6, the risks.
Tolerance, dependence, and withdrawal. This is the dark side of these drugs.
It is. Let's start with tolerance. Simple physiology. If you constantly bombard the GABA receptor with a powerful agonist, the brain's homeostatic mechanisms kick in. The neuron says, whoa, this is way too much inhibition, and it starts to compensate.
How does it do that?
It downregulates the receptors. It literally pulls GABA receptors off the cell surface and internalizes them. So now you have fewer receptors available. That means you need a bigger dose of the drug to get the same hypnotic or anxiolytic effect.
And this concept of cross-tolerance is real too. Very real. Because alcohol, benzodiazepines, and barbiturates all work by modulating that same GABA channel system. If you are tolerant to one, you will be tolerant to the others.
So if a chronic heavy drinker comes into the hospital, they're going to need a much larger dose of Valium to get sedated.
A massive dose, yes.
Okay, now dependence. This is where it gets really scary.
Physical dependence means that the body has adapted to the presence of the drug and has reset its baseline. It now requires the drug to function normally. If you abruptly pull that drug away, especially a short-acting high-potency one like alprazolam or triazolam, the brain is suddenly left in a state of severe under-inhibition.
You've cut the brake line.
The brake line is cut and the engine is revving. The result is a withdrawal syndrome. Rebound anxiety, rebound insomnia that's worse than the original problem, agitation, tremors, and in severe cases, seizures.
And withdrawal from these drugs can actually be fatal.
Yes. Withdrawal from sedative, hypnotics, and alcohol is one of the few drug withdrawal syndromes that can kill you directly, usually through status epilepticus. Opioid withdrawal makes you feel like you're going to die, but benzo withdrawal actually can.
Which is why the rule is you must taper the dose down slowly.
Always taper after chronic use. Never stop abruptly.
And finally, toxicity and overdose. We touched on this at the beginning. Benzos alone have that flat dose-response curve, that ceiling. It's hard to kill yourself with Valium alone.
Very difficult, yes. You'd need to take an enormous dose to induce a coma.
But the real killer is the combination.
It's the synergy. It's not 1 + 1 = 2, it's 1 + 1 = 10.
Yeah.
If you take a benzodiazepine with alcohol or with an opioid like oxycodone, the depressive effects on respiration become synergistic and profound. This combination is the cause of the vast majority of overdose deaths that involve benzodiazepines. They were almost never taken alone.
So let's bring this all home. We have covered a huge amount of ground. We've gone from the GABA receptor mechanics, the key difference between frequency for benzos and duration for barbs.
We looked at the subunits, alpha-1 for sleep, alpha-2 and 3 for anxiety, the principle of selectivity.
We traced the drugs through the liver, warned about those active zombie metabolites, and saw how these drugs can distort our natural sleep stages.
And we explored the alternative pathways, targeting the clock with melatonin, the gas pedal with orexin antagonists, and the serotonin system with buspirone.
So when we put it all together, what's the core philosophy for the listener?
It means we have to respect the profound complexity of arousal. It's not an on-off switch. It's a dynamic balance of multiple intersecting neurochemical systems. We are trying to chemically modulate a state that is absolutely fundamental to survival.
Drugs are interventions in a living system. We're not just fixing a broken part. We are shifting the delicate balance of an entire network.
Exactly. When you prescribe a hypnotic, you are constantly weighing the immediate relief of insomnia against the long-term costs. The distortion sleep architecture, the risk of falls and cognitive impairment in the elderly, and the ever-present potential for tolerance and dependence. It is never, ever a free lunch.
And on that note, here's a provocative thought to leave you with. We know about the subunits now. We've known for a while. We know that alpha-2 and alpha-3 seem to control anxiety separate from the sedation of alpha-1. So, where is the perfect anxiolytic? Why don't we have a pure alpha-23 agonist on the market that just melts away anxiety but leaves you wide awake, sharp, and non-addicted?
That is the billion-dollar question. It's the holy grail. There's a ton of research, but it turns out the brain is messy. The separation of function might not be as absolute and clean in the complex human brain as it is in a genetically modified mouse. Or maybe the compounds developed so far just haven't had the right pharmacokinetic properties. But if someone could crack that code, it would completely revolutionize the treatment of anxiety disorders.
A Xanax that doesn't make you sleepy and isn't addictive, that would literally change the world.
It truly would.
All right, listeners. Your homework, if you choose to accept it. Go open Katsung to chapter 22 and find figure 22:1, the dose-response curves. Really look at the visual difference between the steep linear curve for drug A, the barbiturates, and the flattening curve for drug B, the benzos. That single image is worth 1,000 words.
And then find the GABA receptor diagram in Goodman and Gilman and trace where GABA binds, where the benzos bind, and where the barbs bind. Use this conversation as your conceptual map, but you have to walk the territory yourself by reading the primary texts.
Thanks for diving deep with us. We'll see you in the next episode.
Stay curious.